At the Montana Bureau of Mines and Geology, we make geologic maps. A main component of this endeavor is determining the age of different rock units. For some rock units, we hunt for an amazing little mineral called zircon. Finding zircon is an intricate and technically involved process. These mighty mineral grains are almost as hard as diamond. Unlike diamonds, they are formed near the Earth's surface and are quite abundant. However, they can be very, very small. These grains are about 100 microns across. For reference, a human hair is about 30 microns thick. At 100 microns, or 0.1 millimeters, a sheet of paper is about the same thickness as our zircons. And the width of a fine pencil lead is about 5 times that of our zircon grains. Therefore, finding them is difficult and requires a whole team of scientists. After consulting our maps, our quest starts with fieldwork. For every field area, we target certain rocks for age dating. Commonly, we go into the field with specific target units in mind. Sometimes there are igneous rocks that crystallize zircon from a magma. Sometimes there are sedimentary rocks that accumulated grains of zircon from older eroded rocks. In a large state like Montana with lots of remote and mountainous terrain, we commonly find yet undiscovered units and want to know their age. The first step in the process is carefully collecting a sample and marking its location on our map via GPS. Because zircon is so small and hard to find, samples for age dating tend to be very large, often weighing up to 10 pounds each. This can make for a very heavy pack at the end of a day of mapping. The second step in our process is crushing each rock sample into a fine powder. We start with a jaw crusher to make pea-sized chunks, and then a disc mill to grind the chunks into a fine powder. To avoid contamination, most of our time is spent cleaning the machines. What a great excuse to rock out. Now that we transformed our rock sample into a fine powder, it is time to separate out the zircons. Only a small percentage of the millions and millions of grains of rock is zircon, so this process is quite labor intensive. The first step in the process is a Wolfley table. Another property of our amazing zircon is that it is very dense, on average about 2 times as dense as most common minerals. To take advantage of this property, we pour the rock powder onto this slanted, wet, shaking table. As you can see, the lighter grains will float in the shaking table and be removed quickly. The dense grains, like zircon, will sink and travel all the way to the end of the table where we collect them. From here we dry out the now much smaller sample and spread it out. While it is many things, zircon is not magnetic. So by running a magnet over the sample, we can remove the magnetic grains, further zeroing in on our stubborn zircon grains that remain behind. To continue our quest, we turn to what is called heavy liquids. In particular, methylene iodide has a density that is greater than most of the grains left in our dwindling sample, but less than the mighty zircons. So zircons separate and sink to the bottom, and with careful procedures we collect them. We have now transformed at least a few pounds of rock into something that will easily blow away if you sneeze. We are now in the final stretch of our zircon quest. At this point, we have almost entirely isolated this mighty mineral. Now, under a microscope, we handpick individual zircon grains, finding them based on their shape and transparent, glassy appearance. By placing them on grids, we can prepare many samples on the same mount for further analysis. Our final step before analysis is to mount our zircon grains in epoxy, and polish them to expose our hard-earned grains. This process happens in 5 stages, working from a coarse to fine or abrasive. The final polish is checked for perfection under the microscope. Now we pack up our precious cargo for a trip to a lab in Santa Barbara, California. Here we analyze multiple grains from each sample on a mass spectrometer. Each grain has a different abundance of radioactive elements, and we use the ratio of these elements to calculate the age of the sample. Our efforts to find zircon are well worth it, and the results give us a much better understanding of the geology of Montana. Of course, the quest continues.